So this is a talk in which I've tried to put together works and results which have been done in some years ago, together with more recent results. So my attempt was to put them together within the same narrative, even if originally those works were conceived and driven by probably slightly different motivation. When I finished that, then I look at the talk, I realized that actually I wasn't talking about treatment of model error as I was supposed to do. Because to me, treatment of model error means sort of, let's say, attempt to modify methods so as model error could be better incorporated than the default option. That's why I have decided to erase that word and say that rather probably this is a talk about how to estimate model error. The way how then it is incorporated in data simulation is quite standard. As I say, this is a talk in which I have collected and put within the same, behind the same umbrella, different work, and that I have to definitely thank all of the authors and all the colleagues that I co-author with me the work which I present, and they are listed there. They are also Takemasa and Manuel, they are also in the audience. And Manuel gave a talk yesterday indeed. So in a slide, I would like to summarize what I think are, to me, the view and also the historical things that happened. So I think that in numerical weather prediction data simulation until probably a dozen or years ago, the impact of model error was considered small as compared to the growth of the initial condition error. And, but it's a fact that then the amelioration of the data simulation method on the one hand, together with the increase of the data, but also the fact that we have been more and more interested in a longer time horizon, like the seasonal to interannual prediction, have made that the relative impact of the model error on the skill of the prediction has increased. And it is also known that, this is a point here, it is also known that data simulation, especially when we talk about long run, it often manifests itself, model error, excuse me, often manifests itself in biases, and this also, it is usually seen as an underestimation of the uncertainty associated to the skill, to the prediction. And this is also the reason why a typical way how we deal for model error, not only for the model error, but the typical way we deal for the model error in data simulation using inflation. This is an example from a paper on 2012, so it's certainly the situation has now improved, but this is a scissor phase forecast bias for the SNWF IFS model coupled with an ocean NEMO model. Bias over the here 14 to 23, which give an idea of how spatial dependent and big the bias of this model is. So typically we treat the problem, we have seen this equation often these days, so it doesn't matter, I don't need to repeat it again. So just I wanted to clarify that I put explicit here the vector of parameter to make because it is convenient for what I want to say later, and that vector parameter is now intended to represent the external forcing, the boundary condition, and all type of parameter your model can have, while hex stands for the state vector. Usually this is a chaotic map, this is nonlinear operator which relate to the observation. Typically the model error and the observational error are assumed in Gaussian and distributed according to the two covariants which are given here. The reason why, one of the reasons why we treat this object as stochastic and white in time is because the model error is usually given by multiple sources. So this multiplicity of sources give difficult to design a common way, and so the stochastic approach seems to be general enough and convenient. And this is also consistent with the Bayesian formulation of the data simulation. Then we need to estimate this Q in order to do, and we have to do the best possible. So to see how this can be important, this is an example, very simple example, is linear, it's univariate, and so this autoregressive model which is given here, we observe it in this way, and this is the plot, these are my true error covariants, which are actually variants in this case for the model and for the observations. Here I have the case of perfect model, so I'm running an Kalman-Smutter, and the root mean square error is given by 0.71, and the coverage probability, which is a measure of the uncertainty quantification, is equal to 95%. So this is a measure of how well my ensemble spread is able to capture the truth. So then this is an example in a case in when I do an underestimation of the matrix Q by a factor of 10. What you can see is that, of course, I degrade the RMSE increase and also the coverage probability, so the ability of the ensemble to describe the time dependency of the uncertainty. Conversely, I can do an overestimation of Q, which, as you can see, improved dramatically over the underestimation. This is nothing new, but it's also, it's a way to say that it's better to overestimate than underestimate. And in a way, this also promotes the use of inflation. So, it's better to make a big thing bigger. And you will certainly not be as good as the optimal one, but you can do certainly better job than underestimating. It is also known that what really matters is the ratio between Q and R, because when we do an estimate, it actually, this estimate is based on the relative weights of the two components entering the data simulation process. So this is visualized here, in which I have simultaneously underestimated or overestimated, respectively, in the top and lower panel, the matrix Q and the matrix R. You see, when I do, in both cases, the interesting thing is in both cases, the state estimate quality is the same as measured by the root mean square error. On the other hand, the estimate of the coverage probability, so the estimate of the uncertainty around the state estimate changed dramatically. Again, pointing toward the fact that it's much better to overestimate. And, but what is the conclusion of this simple example is that we actually need to simultaneously estimate, if possible, the matrix Q and the matrix R at the same time. So this point is made even clearer, hopefully, in this result here, in which we fix either Q or R, and we estimate the other by using expectation maximization algorithm. And here I plot the root mean square error and the coverage probability on the left and right. And the experiment are with fixed Q on top column and top row, and fixed R on the bottom row. And you can see, for instance, that of course the best results are always obtained when I fix one of the two over its true value, which is 1. But when I, for instance, put in this top left panel, I put 0.25 for the fixed Q, and then the best estimate I can obtain for R is about 1.6, which give a root mean square error of about 0.8. So again, this point to the fact that it is not really possible to compensate for the misrepresentation of either Q by optimizing R or vice versa. But again, we need to estimate it both simultaneously. Now, all this is nice, hopefully, but this is not what I'm really talking about, because what I will talk about is how to estimate Q. The point of what I think are the key obstacles in the type of problem in climate science or geoscience in general we are dealing with is that, as I said before, there is a large variety of possible error sources, which comes by incorrect parameterization of the physical processes, the numerical discretization. Very common also the fact that we usually neglect scales which the subgrid scale process are neglected, are not seen by our model. The other issue is that the size of the model, and consequently the size of the metrics we want to estimate, is much larger than the data that we have at disposal, which is given by this inequality where D and M stand respectively for the observation and state vector dimension. And there is also the fact that we don't actually have a general dynamical law for the model error dynamics, as opposed to the case of the short time evolution of the initial condition error, which for chaotic system is parametrizable using the unstable directions. So given this, these are, I will say, the objective of this talk is to first see whether the white noise assumption that we did when we deal for model error is always a good one, and second, to see whether we can actually use in an efficient way the data to estimate Q along with time. So for the first point, this is very briefly, so let me assume that I have the model given in this way, again, where x and y are, x and lambda are respectively the state vector and the state of parameter, and vector of parameter. And I want to use this model to describe a process which I'm simplifying, or written in this simplified way, in which I have the resolved scale here, which is coupled with the unresolved scale, which is not seen by the model. Obviously, this is not very general, because I should also add here a terms of account for the extra terms in the resolved scale which are not seen by our model. Then I can formally, writing the solution of this equation in the resolved scale, I can take the external product of that, and I can make the expectation. This is what the uncertainty or the covariance will read as a function of time. So we see that there is a double integral, which takes account of the fact that there is all the correlation inside there. And the important factor which controls the evolution is the difference of the velocity field, which usually are referred to as the tendencies. So to see what this can turn, let's assume that the simple example is the parametric error. In this case, we can derive, under some approximation, we can derive better the equation. In this case, I'm assuming that H is, so there is not a resolved scale. I only have error in the parameter. In which case then I can take the difference, I can linearize, and I have an equation of this sort. The first term is the typical tangent linear evolution of the initial condition, error, plus a term which is the typical model error. So it's an integral term because it accumulates up to the time which you are stopping your prediction. And of course, there is an important term here, which is delta, this delta mu, which is obviously the Jacobian of the model with respect to the parameter, which measures the sensitivity of our model with respect to the parameter that is erroneous. And of course, this also, well, we can speculate that because of the presence of the tangent linear model there, also the evolution of the model error will be affected by the presence of the unstable direction, or which are essentially the largest eigenvector of this matrix there. Interesting, if I then take the external product of this object, that I have an equation like this, which is actually the matrix Q that we want, and if I'm not doing any hypothesis about the time correlation, then I have these two double integral here, which once again testify the fact that in general, model error is time correlated. So now coming back to the question that I had at the beginning, which is more general, which is this one, which I may have error in the parameter as well as error in the resolvent coming by the resolved scales. I can take an approximation of that equation in time, and that's what I did here, which is nothing else than a Taylor expansion, and which is stopped at the first dominant order, which is the second, and this is the second because of the double integral that we have here. So this is nothing special. It's just that I'm no longer assuming that the model error is a white noise process, in which case, of course, the integrand in this equation here will be delta correlated, and one of those integral will disappear, and then when my Taylor expansion will have its first order to be the dominant. And this is the typical situation in which Q usually evolves as being linear in time. Now, of course, I don't have this. If I would know that, I will correct my model. Obviously, I don't know that. So one way of estimating that object is to use the reanalysis, which is something that there has been another talk this morning which used the same approach, in which you assume that you have a reanalysis and you consider that reanalysis to be the best possible representation of the truth, and then you use that as a way to mimic the unknown tendency. And then you can use that to compute that object, which is the one that we have there. Now, there are an important point to make here. There are two important points to do. The first is that here, actually, I'm also including the initial condition error, because I don't know, formally this is initialized in different state. So I'm doing, in a way, an overestimation of the real error, of the real model error, because I'm also including initial condition error there. But similarly, I'm doing that mistake here, because the reanalysis can be as good as it could be, won't be the truth. So obviously, by doing that approximation, I'm also implicitly assuming that, including the model error inside, the initial condition error inside. This is an example in which I include this new matrix Q in an extended Kalman filter, which is compared with the classical extended Kalman filter, which is inflated, and this is the root mean square error, the normalized error variance here as a function of the inflation parameter here, and then this is done for the approach in which we use the matrix Q, which is quadratic in time, tune with the parameter alpha, and then the comparison between the two, which stands a bit better in this new approach. Interesting, the best value for the matrix Q is actually lower than 1, consistent with the overestimation that I just mentioned. The same things have been then done for the ensemble Kalman filter method, in particular for the ensemble transform Kalman filter. This is a comparison, ensemble size, root mean square error. There is ensemble ATKF, the best tune in red line here, best tune both in inflation, multiplicative inflation, and localization. And the green line, which is the second point here, is our approximation in which we had this matrix Q estimated based on the reanalysis and quadratically evolved within the analysis window. And then the blue line is the line in which we sample with a sort of additive inflation, and we sample the perturbation from a normal distribution whose covariance is the one which we estimated based on the reanalysis. Of course, this is done in a filter. So when we talk about time correlation in a filtered formulation, it's not really the proper environment, because a filter doesn't see the window of time. of course, whether or not the model error will evolve linearly or quadratically change how big it will be at the time when we assimilate the data, but we are not really incorporating the time dependence of the model error within the data simulation. To do that, we need to make it smoother. We have done that in the 4D var cases. This is very simple with the Lorentz 3D variable. This is the cost function, of course. Then there are the observational and the background terms. But this is just the model error term. Again, you see the double integral or the double summation when you solve that, you lump that in discrete times. And here is a comparison, mean quadratic error, in which you have the strong constraint for the var, which is when we assume the model is perfect, which stands here. Then we have the true case of weak constraint for the var, but with the assumption that the model error is actually not correlated in time. So one of these true integrals disappear, and we only need to estimate the variance at the right time. And this is done in blue using the covariance matrix of the background, has a tuned covariance matrix of the background, as it has been done, I think, at SNWF in the earlier work by Tremolet. And the alpha coefficient is one that you see here, and this is the blue line there. Then with the red square, we have still the weak constraint for the var, which assume an uncorrelated in time model error, but in which we estimate the covariance using the quadratic law, which is given here. And then finally, in the situation in which we completely estimate the discrepancy between the correlation between a different state within the window using this quadratic approximating law, which is given in the horizontal line, red line there. The second part of my talk, I have this time there, which is, so, and the second part which is still again about how estimating the matrix Q is on the other hand related to how can we use the data now to estimate the matrix Q. So the idea here, which is originated by a work by Manuel Pulido, is the one that we can actually use the model evidence. The model evidence are the likelihood of the data conditioned on the things that you want to, whose effect you are interested to scrutiny. So this is written here as the integral because it's the marginalization over the state vector. But that coefficient theta there, the parameter theta there, can include any parameter or even a different model that you want to condition it with respect to. So the point here is that it is possible to show that the posterior, which comes after by the data simulation process, which is given here by, of course, by the state over the window between 0 and k conditioned on all of the data within that window, represent a lower bound for this object. This is very good because this means that we can actually use the natural outcome of a data simulation process as a way to estimate the likelihood of the parameter of interest. And then this suggests that we can have a two-step algorithm in which we first have the expectation in which we determine distribution Q that maximizes Q, which is given, again, by the posterior, which is the outcome of a data simulation algorithm. And then, of course, under the Gaussian assumption or in the case of high-dimensional system, we are, of course, stimulated to use ensemble-based method. And then a maximization in which we want to determine the likelihood parameter which maximize the model evidence. This has been done numerically using an ensemble Kalman filter to estimate the posterior, and then two different algorithms which that have actually different property in order to find the best parameter. And this has given what we call the expectation maximization, and whose combination with the ensemble Kalman filter has the acronym NKF-EM, and with the Newton-Raphson, whose acronym NKF-NR. This is a comparison here in which we have the NKF-EM on top, the NKF-NR on the bottom, as a function of the iteration. And you can even just focus, this is the likelihood as a function of the iteration. And this is what we want to achieve. So this is the difference, the Frobenius norm between the target Q that we know in this twin experiment and the one that we want to estimate. It must be said that in this specific experiment, Q is diagonal, which makes easier. But in this specific experiment. Anyway. So what is interesting to see is that after very few iterations within what we call the evidencing window, both methods converge. Now this is done in batch. So we are actually not using then, in this work at least, we are not actually using the new parameter to start a new data simulation cycle. We are really computing the likelihood using as much data as possible, and then we are using that data create, to write up the model evidence, maximize the model evidence, and retrieve the best possible parameter. And actually, in this work, we also consider the parameter of the model, not just the statistical model. Finally, I want to talk about another work that we've been done, which is related to this, which is regarding the inflation. Why? Because no matter how good, we will never be that good, but no matter how good we can be in estimating Q and using Q, we always need to have inflation, because typically because of sampling error, nonlinearity, non-Gaussianity. Of course, it's much better if you can do that adaptively, and through the popular method that's been done by Jeffrey Anderson and in the context of the AEKF and by Takemasa Miyoshi in the context of the ATKF. We have recently done a survey of these methods, and we have also rederived those methods using a different approach in this recent paper by Patrick Reines. But the main content of that work was indeed another one, was the fact that we were considering the AKFN by Marc Bouquet as a starting point. That method has been designed to estimate adaptively the inflation as an hyperparameter in the case of sampling error alone. So the scope of that work that then became also a survey of existing inflation method was the one of extending the NKFN in order to cope as well of the model error. So in this NKFN hybrid, that was the result I will show the next slide, the inflation is targeted to simultaneously cope with model error and sampling error. No matter how much the effort that we spent in doing the experiment, the result essentially is that the NKF and the AKF adaptive, both for the one based on Anderson work and the one based on Miyoshi work, perform more or less the same, with only a very marginal improvement with the NKF and hybrid. This is an example of the other figures which are present in the paper. And forget about the dashed line, which is the spread. It's not important. It's important, but it's not important in the short time that I have now. The parameter when the f is 10, they were best tuned, and this is when we have the best, slightly marginal improvement. Consider that this ATKF tune has been tuned for all different type of forcing. So it's very important to see that the three adaptive methods are able to do as good as the best tuned ATKF, which was optimization cost very much. But it's also true that one of the conclusions of that work for us was that further sophistication of a single factor adaptive inflation estimate scheme is unlikely to yield significant further improvement. The conclusion is that we have treating the model error as a stochastic term is convenient and coherent with the Bayesian formulation, but in many realistical problems, it's actually time correlated and its impact grow with the horizon. Of course, this is particularly relevant for the smoother, which is nowadays very important. It is very difficult to estimate the model error covariance, and also because the typical classical state augmentation approaches, they fail to do so because the model error component is bound to monotonically decrease with time in a typical sequential update. We have proposed an alternative method to that, which use the model evidence, and in particular, a computationally affordable way to compute the model evidence. We have done that in a batch, so we are not yet done it in a sequential, which will be probably the most relevant application for the class of problem we had in mind. And then I will conclude by saying that in any case, inflation is necessary for the class of problem we are dealing with, because we are always in the situation of being undersampled and in a situation in which we are assuming Gaussianity when it's not. And even that if we start with a Gaussian using a nonlinear model, non-Gaussianity will definitely appear. And these lead us to devise a new algorithm, which is called NKFN hybrid, which is based on the NKFN from Marc Bouquet, but include also an inflation for the model error. And these are the essential bibliography that I have used for this talk. Thank you. Oh, perfect in time. Without a bell, this is...
Right, yeah, thank you very much.